So we were in lecture 10th where we were discussing the AC powers, and in the previous lecture we discussed the complex power, the real power, reactive power and apparent power. Today very first we'll start some problems discussion. What are the complex power problems? Let us see that. Okay. So the question is, the voltage across a load is given, which is the instantaneous voltage is given, having a maximum magnitude of 60. Omega is the frequency and 10 degree is the angle of the voltage with a negative sign. The current through the element in the direction of the voltage is also instantaneous quantity given, where the maximum magnitude is 1.5, angle is 50 degree, and the frequency of the voltage and current is same, so we can relate that. You have to determine the complex power, the apparent power, the real power, the reactive power, power factor, and the load impedance. These are the quantities that you have to determine. Now see, here we are not given any resistance or reactance of the load. That is the reason at the last we are supposed to calculate what is the impedance of the load. What is the impedance of the load? Only information is given to us that if there is a load Z, then the voltage across it is given and the current which is passed through it is given, and no other information is given to us. We have to compute all the powers and the power factor and the load impedance. Now understand, whenever you are dealing with some AC quantities, this I have told in the lecture class also, that you will be always deal with the RMS value of the voltage and RMS value of the current, because we do not deal with the instantaneous value or the maximum value or the average value. We deal with the RMS value in AC quantities. So when we are dealing with the RMS quantities, we want to convert that into phasor format. So we have 60 volt as the maximum value of the voltage. So 60 by root 2 will give you the RMS value of the voltage, where minus 10 degree is the angle which can be obtained from the voltage. Similarly, if 1.5 ampere is the current, then the RMS current is 1.5 divided by root 2, where the angle is 50 degree. So this derivation we have done, why it is Vm by root 2 and why it is Im by root 2. This is valid for AC sinusoidal signal. So if you have any sinusoidal signal, then the RMS quantities are the Vm by root 2 and Im by root 2. Now the first thing that we need to obtain is what is the complex power. Formula for complex power is the RMS value of the voltage and its product with the conjugate of the current. Current is also RMS. Now here we are putting the VRMS. Now conjugate if we have, then this positive sign will become the negative in the conjugate of the current. Rest it will be VRMS and IRMS. The product of that will give you the complex power. You note down the unit is in volt ampere, because that is the product of the voltage and the current. Now we need to determine the apparent power. You know, the apparent power is basically the magnitude of the complex power. So we have already calculated that 45 volt ampere is the magnitude of the complex power, which is basically the apparent power. Now if you are writing the complex power in rectangular form, so we have the polar form as 45 angle 60, and we obtain that in rectangular form with the real part and the imaginary part, then we can say that the complex power can be written as P plus JQ. So it is the real power and this is the reactive power. So real power is 22.5 watt. Note down the unit is in watt. The reactive power Q is the negative of 38.97. Note down the unit is in volt ampere reactive. It is very important that you note down the unit properly, and while solving the problem you mention the unit, otherwise marks can be deducted, and these unit of the power only will decide whether the power whatever is there in the problem or in the calculation is basically the real power, reactive power, apparent power or the complex power, anything. Now the power factor, which is basically the cosine of the difference of the angle between the voltage and the current. So here we can get from the unit, from the angle of the complex power, that is 60 degree. We have studied the power triangle in the previous lecture. So in the power triangle, we were having the hypotenuse as the complex power, the base as the real power, and the height as the reactive power. The angle theta is here, which is the phase angle between the voltage and the current, which is can be used to determine the power factor. So power factor is cosine of the angle between the voltage and the current. So here you have the minus of 60 degrees, so that we can use it. We are adding 0.5. Now we know that power factor can be positive and negative. If you have a positive here, since you have a positive here, the power factor is leading in nature. If you have a negative sign, then it will be having lagging in nature. Okay. Now also we can say that the reactive power is negative. So if the reactive power is negative, also we can say that the power factor is leading in nature and the reactive power is negative. So from the sign of the reactive power and the power factor sign, both can be used to decide whether the power factor is leading or the power factor is lagging. Now we were asked to calculate the load impedance. So load impedance is basically the voltage by the current, which are the RMS voltage by RMS current in phasor format. So in voltage we are giving 60 angle minus 10 degree and current is 1.5 plus 50 degree. Now note here, we are not taking the conjugate, we are taking only the current. Only in power we take the conjugate. So it will be positive here. Then the impedance we are getting 40 angle minus 60 and the unit is in ohms. Now since the reactive power is negative and the power factor is leading, we can say that it is a capacitive impedance, because you know that for a capacitor the power factor will be leading, means the current will be leading the voltage. From here also you can see that the current is leading the voltage, so obviously it is a capacitive impedance. Okay, so that from the impedance also we can decide what type of load it is. The next problem, you have been given a load whose impedance is Z, which is drawing a 12 kVA at a power factor of 0.856 lagging. Now what does mean kVA? kVA means that it is the apparent power, which is the absolute value of the complex power. The power factor is 0.856 lagging in nature from a 120 volt RMS sinusoidal source. So you have a source here, which the source magnitude is 120 volt, and this is the RMS. It is already mentioned. Sometime it will not be mentioned to you. You have to always take that it is a RMS quantity, because we are dealing with AC quantities. Now this source is given to the load Z. So the Z is basically drawing the power of 12 kVA, which is the apparent power, and the power factor of the load is basically 0.856, and this is lagging in nature. Okay, so what you have to determine: the average power, the reactive power, the peak current, and the load impedance of the load. Okay, now the power factor, we know it is cos of the phase angle between the voltage and the current. Here it is given the power factor is 0.856. So it means we can calculate the value of theta, that is the power angle, with cosine inverse of the power factor, which is equal to 31.13 in degrees. Now the apparent power is given as 12 kVA. It means from the power triangle we can know that if we have the power triangle, the apparent power S is already given to us. So this is the magnitude is given to us, and we know the value of theta. It means that we can calculate what is the real power and what is the reactive power. So real power is the apparent power cosine of the angle, that is the power factor, and the reactive power is S of sine theta. So having known the apparent power, we can calculate the real power and the reactive power. So 12 kVA multiplied with power factor, that is cos theta, will give you the real power. Note down the unit, it is in kilowatt. 12 kVA multiplied with the sine of theta will give you the reactive power. Note down the unit, it is in kVA, kilovolt ampere. Now the complex power S can be written as P plus JQ. So we have been given the value of the magnitude of S and the angle of theta, so that we can convert that in rectangular format. So we have the real part and the imaginary part. Also, we have been given we have calculated the value of P, and we have also calculated the value of Q. So we can obtain the this rectangular format for the complex power. Now, complex power is basically the product of RMS voltage multiplied with the conjugate of the current. So, using this formula, we can calculate what is the conjugate of the current. So, on the numerator, we have the complex power S, and on the denominator, we have the RMS value of the voltage. So, these are all phasor format. So, we are getting the current as 100 angle 31.13. Now note down, this is the conjugate of the current. We are having the conjugate of the current. It means whatever the sign is here, we have to change that sign to obtain the actual value of the current. That will be 100 of minus 31.13. Whereas the peak current we have to obtain, and we know that peak current is equal to root 2 times the RMS current. So here you have the 100 as the RMS magnitude. So you multiply that with root 2, you will get the maximum value of the current, which is 141.4 ampere. Now the load impedance Z is basically Vrms by Irms. Vrms we have been given, Irms we have calculated, and then we can obtain what is the load impedance Z. Now here we can see that the sign of this impedance is basically positive. It means that it is an inductive impedance. Okay, it is inductive impedance. Also, we can see from the value of Q, that is the reactive power, we have a positive sign. These also indicate that it is an inductive impedance. So we can decide what type of load it is there. Now, suppose for example, you need to calculate what is the value of R and what is the value of L. Then we can calculate this R from the real value of the power, because we know that power is basically I square into R. Here the current will be RMS and the power is the real power, that is 10.272. So we can calculate what is the resistance. Also, the reactive power Q is equal to I RMS square into XL. So we can calculate what is XL first, and then XL is equal to omega L. So we can calculate what is the value of inductance. So sometimes the circuit elements need to be calculated. So we can use this power formula. Now next topic that we are going to take is conservation of AC power. So the principle of conservation of power not only applies to AC, but it is applied to DC, which we have seen when we were discussing the DC circuits, that in a closed loop, all the power, if we add up, then that will be adding to zero. So power in the closed loop you will be getting is zero. Means like energy conservation, you will be having the power conservation. Now let us try to understand that in terms of AC power, where we are taking two circuits. One is the parallel circuit and another is the series circuit. In parallel circuit, there are two loads Z1 and Z2 which are in parallel. In the series circuit, we have Z1 and Z2 which are in series. The supply voltage Vrms and Irms is given, which is distributed in accordance with KCL here, and it is distributed the voltage in accordance with KVL here. We will try to understand the conservation of AC power. Now, if we are dealing with the parallel circuit, then there is from KCL we can say that the net current is divided into I1 plus I2, and the complex power, which is VI conjugate, we can put the value of I is equal to I1 plus I2 conjugate. Now we can split up VI conjugate plus VI2 conjugate. So we are getting S1 plus S2 here in terms of the parallel circuit. Now same thing if we are doing for the series circuit, we apply the KVL here. So voltage is equal to V1 plus V2 and the complex power is VI conjugate. Here we are substituting the voltage as V1 plus V2, and then we are splitting up and trying to find the complex power in terms of the load power complex. So what we can see that if you have n number of loads, okay, still Zn, then the complex power S, this complex power is being given from the supply end. So the supply is giving this complex power, and these all S1 plus S2 to Sn is being consumed by the load. So that is the conservation of AC power when you have too many impedances connected either in series or in parallel, the conservation of AC power will be there. So what we can say from this statement, the complex power, real power and the reactive power of the source, so it is coming from the source, is equal the respective sum for the load term, individual load term. So it is not only dealing with the complex power, it deals for the real power and reactive power also. So since the complex power we have taken into account, the real power and reactive power will also be conserved, and in that case you can substitute the P is equal to P1 plus P2 plus Pn, which we have taken in case of a DC circuit, because in DC circuit you will not have any reactive power, so reactive power will be zero in DC circuit, so there only real power was there. Similarly, if you have the reactive power Q, then you will be having Q1 plus Q2 dot 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 till Qn. We'll take one problem to understand. Now let us take a source of 220 angle 0. Now this voltage is the RMS voltage. Now you have a line through which the current is being flown. The line impedance is given as 4 plus J2 and the unit is in ohms. So this is ZL, line impedance. And here you have the load which is forming in the form of this is line and this is load impedance. Load impedance is equal to 15 minus J10 ohms. Now the first thing that you need to see whether all the quantities are in ohms or not. If it is not in ohms, as I said in the AC circuit, you have to convert that into ohms, means whether it is an inductor or a capacitor, that you need to convert in XL and XC. Second thing, if the voltage is given in instantaneous quantity, you have to convert that into RMS quantity, and then only you can do whatever unknown you need to find out. Okay, so let us try to find out what are the unknowns. So the total impedance of the system, which include the source and the load. So we have a transmission line 4 plus J2 impedance, and we have a load impedance of 15 minus J10. So both are in series, we can add up and we can find out what is the net impedance of the entire system. Now the current which is drawing from the source can be obtained from the Ohm's law. So we have the voltage divided by the total impedance of the system. So we are getting the current as 10.67 angle 22.83 degrees. So we have obtained the total impedance, we have obtained the net RMS current, and the net RMS voltage is already given to us. It means the source power is basically the complex power, a complex value of the voltage, that is the RMS, and the angle multiplied with the conjugate of the current. So here we have obtained the current, we have to just take the conjugate of that and multiplied with the phasor form of the voltage. We will be getting the complex power. So complex power you will be getting in the polar coordinate. Convert that into Cartesian rectangular coordinate, you will be getting the real power and the reactive power of the source. So since we have a negative sign in the reactive power, the load is leading power factor. So load is at leading power factor. Now let us deal with the line first. So the voltage of the line, or here the voltage of the line that we need to, sorry, impedance of voltage of the line. The voltage of the line will be V is equal to Z, impedance of the line multiplied with the current. Now it is a series circuit, so same current is flowing through the system. So impedance is given 4 plus J2 and current we have already obtained. So the net voltage of the line is basically 47.72 angle 49.4. It means we can calculate the complex power of the line, which is voltage multiplied with current conjugate. Only difference is that you will be taking the line voltage here. Current is same because it is a series circuit. So from the rectangular system of the power, we can obtain what is the real power and the reactive power. So 455.4 is the real power and 227.7 is the reactive power. The same or a different way is that the complex power of the line, we can write it in the form of the square of the current, that is the magnitude of the current square multiplied with the impedance of the line. So we will getting the same answer. That is the real power is equal to 455.4 and the reactive power is 227.76. So we can use this formula to calculate the real power and the reactive power, or we can go by this formula. Both will give you the same answer. Now we'll be dealing with the load. So load impedance is given to us. Current is same throughout the system. So we will get the load voltage. After getting the load voltage, you can determine the load power, complex power, and then you can obtain what is the real power and reactive power of the load. Now here you have a negative sign that indicates it is a leading power factor load, and the unit is in volt ampere reactive for reactive power and watt is for real power. Now, what you can note down here is that conservation of power indicates that the source power, complex power, is equal to the sum of the complex power of the line plus complex power of the load. So if we add the line power and the load power, we will get the complex power of the source. So this is in accordance with law of conservation of power. Also, we have to note that always we are using the RMS value of the voltage and the current. So throughout the AC system, please note that you use the RMS value only to do the calculation always. Next topic will take the power factor correction. Okay. Generally all domestic loads, like for example, washing machine, air conditioners, refrigerators, or the industrial loads like induction motors are inductive in nature. So the load will be inductive in nature. 95 to 97% of the load that are there either in the domestic appliances or in the industrial appliances are inductive in nature. Now you know that for an inductor, the current will lag the voltage. So the power factor will be lagging in nature. So the power factor will be lagging in nature. Reactive power will be positive. Reactive power will be positive. It means the low lagging power factor is there. So if the value of XL is more then the power factor will be less. So it will be lagging power factor condition, which is not good. Now why it is not good, that we are going to discuss. Now, although we know that inductive nature of the load cannot be changed, we can't change the washing machine, we can't change the air conditioner or the refrigerator or the induction motor. So nature of the load cannot be changed. What we can change? We can change the power factor. So we can increase the power factor. We have to increase the power factor. You know that power factor lies from 0 to unity 1. So this is the unity power factor condition. This is, if you go in this direction, it is a low power factor condition. If you go in this direction, that is high power factor. Okay. Now, when the inductive load is there, you are going in the lower power factor condition. But that is not good because the power factor will be less and you want to increase the power factor. Now, these also we are going to study, like why we want to increase the power factor. That is known as power factor correction method that we are going to see. So what is power factor correction? Power factor correction is a process of increasing the power factor without altering the voltage or the current. So you are not going to change the voltage. This is the supply voltage you are not going to change. This current will change a little bit with respect to the parameters that you are going to take. So that we are going to see. To the original load means if you have the load impedance ZL, which is equal to R plus JXL, it means that whatever the voltage is across the load or whatever the current which is drawing the load, you keep that to be conserved. That voltage or current will not change. But then also we are going to increase the power factor with a certain process that is known as the power factor correction, and which is very important. Now what is that? Let us try to understand. So we have discussed that most of the load are inductive in nature. It means that the load is a combination of resistance and the reactance, which is taking the power voltage Vrms and taking the current Irms or the inductive current of the load. Now, if I want to have the power factor correction, it means I want to increase the power factor which is very poor or low. Then what I can do is that, you know that when XL is there, the Q value will be positive. So if we can have some Q which is negative, and these negative Q and positive Q cancel out each other, then we will be having a good power factor condition. So how it is possible? Let us see. So this inductive load Q is giving you a positive reactive power. If we add a capacitor which is having the Q to be negative, and this negative Q and positive Q is balancing each other, it may not be balancing entirely, but it will try to improve the value of the reactive power, then you will be having a good power factor condition. Now how it is, let us see. So the current which is drawing from the source on and the load and the source voltage V will be same across the load impedance VL as well as the capacitor VC, because they are in parallel. Now this current I which is drawing from the source, you see the current IL was drawn by the load when there is no capacitor. Now due to the presence of the capacitor, the current IL remains the same. So the current which is there for the load without a capacitor and with a capacitor are same, and there is a current IC. So we know from KCL that the current I is equal to IL plus IC. By changing this IC value, we can change this current I, because these we will not touch. This current will be same and the voltage will be same. So we have to adjust this capacitive current so that this current is changing. Why this current I need to change? Because you know that power factor is basically the angle, the voltage and current, the cosine of the angle of voltage and current. So if the cosine of the voltage and current angle, that is theta, that angle I need to improve it, because you know that the theta, if it is increasing, the cos theta will decrease. Okay, cos of 0 is equal to 1 and cos of 90 is equal to 0. We want close to 1, not close to 0, right? So that is the reason we are adding a capacitor in such a way that the current which is drawn by the capacitor is modifying this current which is drawn by the load, keeping the load current to be the same. Okay, now if I draw the phasor diagram, on the x-axis, the reference axis, we have voltage. It means V RMS angle 0 degree. So this is the reference voltage. Now we have an inductor and a capacitor. You know that capacitor current is leading the voltage by an angle of 90 degree. So capacitor will lead the voltage by 90 degree. Now the inductive current, which is due to the inductive load, it is having two components. One is the resistance and it is having also the reactance R plus JXL. Now this current I will not be entirely at minus 90. Okay, this is due to the presence of this resistance. Okay, it will be at an angle of theta 1. So theta 1 is the angle which the supply voltage V is making with this current IL. Okay, now when we are introducing this capacitor C, IC, what it is having, it is taking the current IC in such a way that it is drawing less current from the source I. So this current IC, if we have the vector here IC, then I am getting the combination of, because I am having the source current I is equal to vector sum of the load current IL plus the capacitor current IC. So I am having the load current here and this vector I am shifting it here IC, then I am having the current I here, that is the source current. Now the angle theta 2 is the new angle between the voltage and the current due to the presence of the capacitor. So what is happening, due to the adding of the capacitor, the phase angle has changed from theta 1 to theta 2 and it has reduced. So if the phase angle has reduced, obviously the power factor will increase. So power factor is increased without touching the voltage, without touching the current of the load. So with the same voltage, the current decreases, means the net supply current decreases. So you will be having less electricity bill, because if the power factor is poor, what will happen? The current drawn by the system will be more. If the current drawn by the system is more, then the loss I square R will be more and you will have more electricity bill. So if you want to reduce the electricity bill, you will be not able to change this load. because these load are fixed, what you can do is that you can have the power factor correction in such a way that whatever the current which is drawn from the source, that current and this voltage, the angle changes and the magnitude of the current changes with the introduction of this capacitor. We will try to understand this concept by a little bit different method, which is mathematically. Okay, let us see. On the x-axis or the real axis, we have the real power P. On the imaginary axis, this is your imaginary axis, we have the reactive power Q. Okay, this is x and this is y. Now, earlier the system was operating at a power factor of cos of theta 1. This is earlier when no capacitor is there. Now with the introduction of capacitor, the new power factor has become cos of theta 2. So what has happened when the power factor has changed? So the real power P can be written as S1 cos theta 1. So S1 is the original complex power when the power factor is theta 1. So we can write P is equal to S1 cos theta 1. Now the reactive power Q1, the original condition we can write it is equal to S1 sin theta 1 or P tan theta 1. Any formula we can use in terms of sin or tan. Now, with the introduction of a capacitor, we have introduced a capacitor, we can write what is the value of the Q2. What is Q2 here? Because of the capacitor. Now here, the real power is constant. P is constant. It is not changing because on introduction of C, we can only modify the Q. We are not touching this real power. So the Q2 is equal to P of tan theta 2. So theta 2 is the now new power factor that is due to the presence of the capacitor. So due to the presence of a capacitor QC, I can have Q1 minus of Q2. Q1 is the power factor. Q1 is the reactive power when there was no capacitor. Q2 is the reactive power with the introduction of the capacitor. So this QC we can determine which is Q1 minus Q2, or in terms of real power we can write P of tan theta 1 minus tan theta 2. We know that the reactive power is equal to V RMS square by XC. That is the reactance of the capacitor. We can also write this in terms of omega C V RMS square. It means that what is the capacitor we can use so that we can improve the power factor. So the capacitor that we are going to use is P of tan theta 1 minus tan theta 2 divided by omega V RMS square. Frequency is given to us. RMS voltage of the supply is given to us, which is constant. We want to keep the real power constant. Theta 1 was the phase angle between the voltage and current without the introduction of a capacitor. Now, what amount of power factor we want to improve, that is theta 2. Okay, so that we will get what is the capacitor we have to introduce in the parallel to improve that power factor. Means I want to get a power factor angle from theta 1 to theta 2. Then what is the capacitor that I need, that I can calculate from this formula, right? Similarly, in some system what is happening is that your power factor you want to decrease. You do not want the power factor to increase, rather you want to decrease in power factor in some application. So here you are using a capacitor, there you will be using an inductor. So the QL value you can use it, and then you can use the value of the inductor. So due to the presence of the inductor, the power factor can be brought down. Why you want to bring down the power factor? Because for example, if you have a synchronous condenser, this is a device synchronous condenser which is operating at a leading power factor. So Q value is negative. I want a positive Q so that these cancel out each other. So I will be using a inductor. So the inductor value will be V RMS square divided by omega times QL, where QL is equal to Q1 minus Q2. This is the this power factor 1. There is the inductive the reactive power for the first condition when there is no inductor, reactive power in the second condition when there is an inductor. So case to case we need a capacitor or an inductor so that we can have a good control over the power factor. So we have understood that if we increase the power factor, it means we can control the supply current, and by controlling the supply current we can have less losses. I square R loss will be less. We'll solve one problem to understand that. Now, there is a load which is connected across a 120 volt RMS supply voltage. The frequency of the line is 60 Hz. The load is absorbing a power of 4 kilowatt. Now see the unit, it is in kilowatt, so it means that this is the real power P. The lagging power factor condition is given as 0.8. So power factor is lagging in nature. Find the value of the capacitance necessary to raise the power factor to 0.95. So cos of theta 1 was 0.8. Now cos of theta 2 you want to increase to 0.995. So the lower value is 0 and the higher value is 1. So you are moving towards the unity power factor condition. If you are moving towards the unity power factor condition, it means you are improving the power factor. So from the power factor condition 1, cos theta 1 is 0.8, you determine what is the value of theta 1 first. This is the angle. Now you can determine the complex power S1, that is the initially we have drawn the triangle concept. Let us draw it again. So your triangle is like this. This is at S1, which is operating at an angle of theta 1 with the real power constant P, and the reactive power here it is having Q1. So S1 is equal to P of cos theta 1. You will be getting 5000 volt ampere. So S1 is operating at 5000 volt ampere. Now the reactive power Q1 is S1 of sine theta, which is 3000 volt ampere reactive. Now the new power factor is 0.95, which is giving angle of 18.19. So now the new angle theta 2 here is 18.19, which will be having a new complex power S2 and a new reactive power Q2. So this power is compensated QC due to the capacitor. So when the power factor is raised to 0.95, real power do not change, it is constant, and the apparent power has changed, which we have to obtain it. So this is the apparent power that is changing. So S2 is at 4210.5 volt ampere. It was at 5000 volt ampere under the first condition. So we can see that the apparent power has come down. So apparent power has come down. Now the new reactive power Q2 is equal to S2 sine theta 2, because we are having a new angle theta 2. This is your S2 and this is your Q2. This is constant power P. So you can obtain the reactive power Q2 here, in which is equal to 13.14 volt ampere reactive. If you note down, the Q1 value is at 3000 volt ampere reactive, which has come down to 1314.4. So you have been able to reduce the reactive power of the system. The difference between the new and old reactive power is due to the parallel addition of a capacitor to the load. So you are having a load impedance ZL and you have added a capacitor in parallel, and that is in parallel with a source which is VRMS. So QC value, which is compensated, is equal to Q1 minus Q2. So this amount of the reactive power you have compensated, and the capacitor that need to be placed in parallel that we have to determine is QC divided by omega RMS square, which will give you 310.5 microfarad. So you need a capacitor of 310 microfarad so that the value of theta 0.8 has reached to 0.95. So you will be having the less reactive power and you will be having a better power factor. Then electricity bill will also be less, the losses will also be less. So you need a 310.5 microfarad capacitor to be connected in the system. So these complete the AC power analysis, covering all aspect of the AC power.